So in this video I'm going to be talking through the first task of the ISP on Unit 1 materials. Task 1 is what we're looking at. So if you scroll down, we look at task 1 is about density, mass and volume. We're looking at the physics of flow and how forces acting on an object change as it reaches terminal velocity, so including the idea of Stokes' law. The AA star principle is talking about how flow links with air resistance. So remember, you've got the idea of Stokes' law, which causes the drag force. And remember that only works in laminar flow, though Stokes' law only works for laminar flow, not for turbulent flow. Right, so let's get straight stuck into the explaining everything tasks for task 1. So we go, it says define the following terms using diagrams where appropriate: density, laminar flow, streamline flow, terminal velocity, turbulent flow, upthrust and viscous drag. Okay, so remember, density is a mass per unit volume. Okay, so as an equation, the density is equal to mass per unit volume. Okay, so it's kilogram per unit volume, so it's per meter cubed. Okay, that's what I mean by density. Laminar flow is flow with no abrupt changes in motion. Okay, so no abrupt change in motion, no mixing of layers essentially. Streamline flow is the same as laminar flow, no difference between the two. Terminal velocity is the fastest speed at which an object can move, and it's when all the forces acting on the object are balanced. So if we have 3 forces acting on an object, say this is a falling object, you have the idea of upthrust, you have the idea of the viscous drag, which I'll call F, and we'll have the idea of weight. Okay, so initially remember, weight is the only force acting, so weight is greater than upthrust, and there's no viscous drag when there's no motion. So when it says first drop, there's no motion, therefore no F. So weight is originally greater than viscous drag. So remember, there's an unbalanced force here, so that leads to an acceleration. As the acceleration happens, the velocity increases. The increase in velocity leads to F to start to increase, okay, and that keeps going on until the weight is equal to the viscous drag plus upthrust. Okay, so that's our idea there. When we get to that point, sorry, that's a V there, it's a U there. Okay, when it gets to that point, that's the point of terminal velocity. So that's how you can explain terminal velocity. So remember, use words as you're doing it, don't necessarily just use the equations as I have there. Okay, so turbulent flow, okay, so that's flow with abrupt changes in direction. So that leads to this idea of drag. It leads to this idea of objects finding it difficult to move through. So there's abrupt changes in motion. Remember, Stokes' law cannot be applied in this situation. So it doesn't lead to drag. Stokes' law cannot be applied in this situation, essentially is the idea. So as it goes towards this ball, it ends up with turbulent flow, so you can see the layers mixing. So mixing of layers takes place. Upthrust is equal to the weight of a fluid displaced. Okay, so upthrust is equal to the weight of fluid displaced. So upthrust is equal to the weight of the fluid displaced. Okay, so remember, weight is equal to mass times by gravity, so it's the mass of the fluid displaced. But mass, if we look back at our original equation for density, so just get that back into shot, mass is equal to density times by volume, so we can rearrange that. So density, so upthrust can also be equal to density of the fluid times by volume of the fluid displaced times by g. The final idea there is the idea of viscous drag. So again, that's the force that opposes motion. Okay, so similar to air resistance, force that opposes motion. Okay, so describe Stokes' law and Archimedes principle. Show the two can be interlinked. Okay, so Archimedes principle is this idea of upthrust, that upthrust is equal to the weight of fluid displaced. Stokes' law is, let's get that into shot, there we go, is equal to this equation here. So I define all the terms of this equation. So that's the viscous drag, that's 6, that's pi, 6 and pi over there. The r is the radius of this object that's falling, so we have to assume that everything's circular in this situation. Eta, the symbol here, is the viscosity of the substance, and that is the terminal velocity. Okay, so we've defined each of the terms there. So viscosity, remember, is essentially is how thick something is. So higher temperatures lead to lower viscosities, therefore higher velocities. if something gets heated up, things don't move through it quicker because it's got more energy. That's incorrect. The reason why things move through it quicker is because it has a lower viscosity. So if you think about something going through oil or honey, it will move through it faster at higher temperatures because of the idea that the viscosity is less. So you need to know that as the temperature increases, the viscosity decreases, and that leads the velocity to increase. Okay, T in this situation is temperature. Usually we use this symbol for temperature, theta. Right, okay, so I've defined Stokes' law and I've described Archimedes' principle, showed the two are interlinked. So that goes back to what we're talking about over here. Remember, that comes from Archimedes' principle, that comes from Stokes' law. Okay, so the two added together for a falling object will be equal to weight. Remember, if the object is rising, okay, that won't be the case. If the object is rising, up thrust will be very large, weight will be very small, and viscous drag will act in the opposite direction this time. So in that situation, up thrust is equal to weight plus viscous drag at terminal velocity. Well, there we go. So up thrust is very large, weight is small. We've got the idea of viscous drag being quite large. So these two added together will equal that for terminal velocity. So up thrust is equal to weight plus viscous drag. Okay, so let's get stuck into these questions. Skip down. Here we go. All right. Okay. So first question. Okay, the velocity of a ball bearing falling from rest through a syrup would something with the decrease falling. So originally the velocity is going to increase, it's going to accelerate, but then it will reach stay at a constant, a non-zero value. Remember, because the fact it reaches terminal velocity. So the idea is it decreases linear from zero. That's not the case. It won't decrease linearly. It increases from zero to a maximum. If it's initially at rest, it will. It says falling from rest through syrup, so originally be at rest and it reaches a maximum, so B sounds right so far. C increases linear to zero. That doesn't seem to make sense because that will mean it will start at a minus value to begin with. Sorry, increases linearly from zero, it says, so it would keep going on forever, and we know that isn't correct. Stays constant at a non-zero value. Well, that isn't correct. It's not going to be a constant velocity throughout, so it must be B. Okay, so we've got a verse from a meteorologist in terms of Permian wrote over here. Mentions the word walls in there a few times. Big walls have little walls which feed on their velocity, and little walls have lesser walls, and so on to viscosity. Describe what the author meant by the word wall. So walls are like eddies. So these are areas of turbulent flow. That's what those mean. Okay. So they want diagrams and descriptions of laminar and turbulent flow. So remember, if we look at turbulent flow, you've got the layers mixing. So I'll just draw another one to show that over here. You've got the layers mixing like this. At least 3 lines, and laminar flow, remember, straight lines going through. So no mixing of layers for laminar flow, mixing of layers for turbulent flow. As straightforward as that. So 2 marks for each. Turbulence can be used to reduce the rate of flow of fluid. Explain the statement in terms of energy transfer. So remember, when there's more turbulent flow taking place, there's going to be more resistance to motion, and therefore there'll be a greater amount of energy lost due to heat. Okay, so that's the idea. So let's check questions 1 and 2. So B, yep. So an eddy, a circular flow. We talked about that idea. Okay, laminar, at least 3 parallel straight lines. Okay, no abrupt change in direction. Okay, exactly what we're talking about. So no mixing of layers, and then mixing of layers taking place for turbulent flow. Idea of kinetic energy. So that's what we're talking about. The idea of the motion. Slowly becomes less and less ordered, becomes more and more disordered. So essentially, it becomes thermal energy afterwards. So the more disordered energy is, the more it becomes into thermal energy. So overall, the kinetic energy reduces and the flow slows down. It's exactly what we were talking about. Right, question 3. So if I remember correctly, this is a question about a stone in wine, or an object in wine. Let's have a look. Here we go, yep. So wine is being fermented and contains small particles. These small particles have to settle so that they can be separated from liquid. Add the diagram to show the other 2 forces on a particle falling within the wine. So it's going to fall, force it back down. So here we go. There are the forces over here that we need to draw on it. So I'll draw it on the other fresh sheet. There we go. So we've already got up thrust. Now the other forces, if it's falling, we want to add to that plus a viscous drag. Okay, so add it like that. Add it next to it, plus viscous drag. Then down, add weight. Don't necessarily do 2 arrows. Do the 1 singular arrow like such. And just say that becomes up thrust plus viscous drag. So up thrust plus viscous drag like that. Make it nice and clear. The F isn't very clear. There we go. Right. They're not asking for an expression or anything, are they? Let's just double check. Add labelled arrows as diagram, so to show the other two forces. Done that. Brilliant. Okay. The upthrust can be calculated using the expression 4 pi over 3. So 4 over 3 pi r cubed. So that's a volume times density times gravity, where density is of wine and r is the radius of falling particle. Explain how the above expression for upthrust is derived. Okay, so we went through this as part of the explaining everything. So upthrust is equal to the weight of fluid displaced. Okay, so therefore that's going to be equal to the mass of fluid displaced. You can just use FD to demonstrate that once you've written it once, times by G. Well, mass is therefore equal to density times by volume. So the upthrust is now equal to the mass of the fluid displaced times is equal to the density of the fluid displaced times by the volume of the fluid displaced times by G, and with that volume is equal to 4 over 3 pi r cubed, so we can sub that in as well now. So you end up with upthrust being density of the fluid displaced 4/3 pi r cubed, with that being the radius of the fluid displaced, in other words the radius of the object, times by G. And that's exactly what they've got there. So because we've got the fluid displaced, we can replace the fluid displaced idea with wine. Okay, because that's less they're using. So there we go. It's exactly what they've got. We've got the same expression now. It's a nice 2-mark question to get. Write the expression relating to 3 forces acting on a particle when it reaches terminal velocity. Well, we know that. Okay, hold on. I've just realised you haven't seen much of the derivation. So let me talk through that again. So upthrust. Might need to zoom out slightly actually. There we go. So, or maybe a bit too far. There it is. Actually, I tell you what. For this question, so I'm going through the previous question still, the one about the expression for upthrust. I'm going to make the screen a bit bigger and I'll zoom out a bit more. So right, upthrust is equal to the weight of fluid displaced. Okay, so therefore upthrust is equal to mass times mass of fluid displaced times by gravity. So fluid we're talking about is wine, so you can replace it with W at any point if you want. We got this because weight is equal to mass times gravity. Okay, so that's what we've all replaced. That's the only thing we'll replace there. Well, mass is equal to density times volume, so we can replace that. So put in density and volume of the fluid displaced. So again, that's just of the wine. Then we've got the idea that a volume is equal to 4 over 3 pi r cubed. So we can place that in. Once you sub that in, you end up with the final equation of this. Okay, so remember when this situation over here is at terminal velocity. So this is the next question now. The expression that they're after, the weight is going to be equal to F add U or U add F. So viscous drag add the upthrust. Okay, let me just shrink that down now. Okay. Show how the terminal velocity of the particle V is given by the following expression. Right, so we're going to have to rearrange for V now. Horrible question. Absolutely horrible question. And not worth very many marks, only 2 marks. Okay, so I'm being honest with you, it's not the nicest question to get. But let's get to it. Okay, it is not the trickiest thing to do once you actually get used to manipulating equations. What I will say is it will take up pretty much the rest of the sheet of paper to lay out neatly. So once again, I shall make it bigger so that we can see this clearly. Okay, so the first thing we need to do is we need to think about the expression that we had from before. So weight is equal to viscous drag plus upthrust. Now we need to sub in what we know. Okay, well we know the viscous drag equation for Stokes law, so 6 pi r e to v, we know that. And then we also know the equation for upthrust, which they told us already, is 4 over 3 pi r cubed density of wine G. Okay, so that's written in a slightly different order to the way I did it, but it's the same. You can multiply in any order and it's fine. That is equal to the weight, and we know that weight is equal to mass times by gravity. Okay, so if we flick back for a second in terms of what they want, well, they don't want any mass in it at all. There's not a single bit of mass in here, but they do have everything in terms of density. So let's get rid of all our masses and get everything in terms of density. So the only mass we have over here is this one over here. Let's replace that with another density. So that's going to be density times by volume. Well, that's going to be the density of the solid. That is the weight of the solid. That's going to be the density of the solid times by volume. And we've got G. We've got 6 pi r e to v plus 4 over 3 pi r cubed density of the wine g. Okay, so it's looking quite long and quite disgusting as an equation right now. Let's simplify this right hand side of it. Okay, so is there any terms right now in both? Well, we've got this idea of pi and r in both, but if we look at what they want the densities, okay, together. So let's get the densities together first. Okay, that's clearly what they want us to do. So let's get the densities together. So let's take this idea of a 4/3 pi r cubed density of wine g and bring it over onto this side over here. Okay, so we can, because the whole of this is being added on this side, it can just be taken away. Okay, so I've written the same as before so far. There we go. And then we're just going to take away from that 4/3 pi r cubed density of wine g, and that is equal to 6 pi r eta v. Now let's simplify this. So they wanted the densities by themselves, so you can see that we can pull out v and g for each of these. Well, that's got a v in it as well, so these v's are technically the same. Remember, the volume here is 4/3 pi r cubed, and that is still 4/3 pi r cubed. So let's pull out 4/3 pi r cubed for both of them. So that and the whole of that cancels for both of them. Okay, and there's also g, so that also cancels for both of them. So what you actually end up, well, I say cancels, comes out of the bracket. So what you actually end up inside the bracket is this idea over here, and you end up with 4/3 pi r cubed g outside of it, and that is equal to 6 pi r eta v. Well, they want an equation for v, so we need to bring all of this underneath. Okay, so let's take this chunk and bring it underneath. So it's looking very, very long and very, very horrible right now, but we're nearly there. I'll zoom into this last little bit so you can follow it through a bit clearer. Oh, there we go. Okay, so we've got 4/3 pi r cubed g, density of the solid minus density of wine, divided by 6 pi r eta, and we're going to leave v over there. Now we've got to look for our cancelling outs. Well, pi's cancel, r cancels with one of the r's over here, so it becomes r squared instead. Then we've got this idea of 4/3 and 6. Okay, so if we did that, that's the same as doing 4/3 times by 1/6, so you actually end up with 4/18. So 4/18 cancels to 2/9, so we cancel out to 2/9. And then if you look carefully at what we're actually given beforehand, what they wanted us to get to, let's pull this down, that's exactly what they wanted us to get to. So you end up actually over here with 2 r squared g, density of the solid minus density of the wine. So I'll bring this back into shot now. There we go. Over 9 eta. Horrible, horrible question for 2 marks. In my mind, that should be 3 or 4 marks. Unfortunately, you can see over here, it is just a 2-mark question. Never mind. Okay, so explain how do you expect the velocity of this particle to change if the temperature of the wine was increased. So if temperature of wine was increased, viscosity would go down. Okay, so the velocity would increase. So the velocity would increase because the temperature, because the viscosity would decrease, therefore the velocity would increase. Stokes' law is only valid if the flow is laminar. Okay, using a diagram we explain what we mean by laminar flow. Done it before, not going to go through it again. Okay, there in every single question. Next, okay, so some people think that raindrops fall at the same speed, others think that their speed depends on their size. Calculate the speed of a raindrop if it has fallen, oh, let's bring this work on smaller. Okay, if it has fallen freely from rest for 0.2 seconds. Okay, so you've got multiple ways to approach this. You might need to use some of the mechanics equations that you've got. That's the easiest way to do it. So if it's falling from rest, remember we've got the idea of v being the final velocity. That's what they want. That is what they want. The initial velocity is going to be 0. Acceleration is going to be 9.81 or minus 9.81 meters per second squared. That's meters per second, I should put in there. And t is 0.2. So the equation of motion, seconds. The equation of motion, oh, sorry, there you go, now we can see that clearer. And a bit of zoom. And hopefully a bit of focus. There we go. Okay. So hopefully you remember that acceleration is equal to change in velocity over time. Okay. So we need to rearrange that for initial velocity. So initial velocity is equal to u plus at. So remember that's there on the equation list if you need it as well. So that's just 0 plus 9.81 times 0.2 seconds. I'll just whack that through our calculator. It's going to be 19.62, which is a common value. Sorry, 19.62 divided by 10. So that's 1.96. It'll be. Let's just double check that though. Yeah, 1.96. So remember, 3 sig fig is what we normally record to in terms of our answers. Don't go beyond that. Let me just move my laptop across so I can get this a bit better into shot. There you go. There we go, focus there. Okay, so you can see that clearly how I figured that out there. So 0 and 9.81 times by t. So you just multiply those two things together as you do it. So it says over here, explain, sorry, the raindrops fall so longer than 0.2 seconds. Explain why its acceleration does not remain uniform for the whole of its fall. Okay, because of the fact, remember, that the size of viscous drag is increasing. Because of the size of viscous drag increasing, the resultant force changes as well. And if the resultant force changes, the acceleration will change as well. So that will mean it will reach its idea of a terminal velocity, where all the forces acting on it are constant, which means that it will stay at a constant velocity. So all the forces acting on it are in equilibrium, so in other words it will balanced, so it'll have no resultant force, so therefore it will go on at a constant velocity. There'll be no acceleration. To show that the mass of a 0.5 diameter spherical drop is less than 1 times 10 to the minus 7 kilograms. 0.3 meters cubed of water has a mass of 1 times 10 to the 3 kilograms. Okay, so they want us to show the mass of 1.7. So they want us to show a mass of a 0.5 millimeter diameter raindrop. Well, if you've got diameter and you want to get to mass, you're going to need to know a couple of things. You know you're going to need to know. You know you need to know density, and you know you need to need volume. Well, volume is quite easily calculatable from diameter. You just need to get into radius and then 4/3 pi r cubed. But what about density? Where are we going to get that from? Well, they're telling you the density of 1 meter cubed of water. Okay, well, that is the definition of density: mass per unit volume. So mass divided by volume. So it's 1,000 divided by 1. So the density of water must be 1,000. We know that as a value as well. Density of water is 1,000. Okay. There we go. Right. This is going to make this quite straightforward now, because we know that density is mass divided by volume. So mass must be density. Mass must be density times volume. So mass must be 1,000 kilogram meters cubed times the volume. So the volume we've got here. That's the, that is the density. So the volume we've got here is 4/3 pi r cubed. So what is our r? Well, our r is half this diameter we've got. So that's 0.25 millimeters. Well, millimeters times 10 to the minus 3. So it's going to be 1,000 times by 4/3 pi times by 0.25 times 10 to the minus 3. But only this part of it is squared. So note the sheer number of brackets I've got in here. Because of my old calculator, I need to write it in with those sheer number of brackets. Okay, so let's watch it through carefully on my calculator. So 1,000 times by bracket 4 divided by 3 times pi bracket 0.25 exp minus 3 bracket squared bracket 1.6 times 10 to the minus 4. Oh, it's quite clear the mistake I've made. That's a squared. It should be a cubed. Okay, Silly me. So let's go back through that and change that. Oops daisy. I don't want to press AC because that will... Oh no, it doesn't clear it, that's fine. Okay, so let's put it in correctly. Just trying to remember how to do it. Oh, there it is, cubed. I haven't done this calculator in a while. Okay, so 6.5 times 10 to the minus 8. Oh, again, something's a bit off there. I'll just double check with the marks, see what I've done wrong. It's possibly my calculator, knowing this calculator. Let's just check that I was talking about 4.3. It probably is doing 4.3 times by pi. So it's probably doing the end of it right. So let me end of it wrong. 4.3 times by pi. Hold on, let me actually. Yeah, I can tell it's already doing this wrong. It's doing the 4.3 in the wrong place. The ancient calculator does not help. So let's do pi here multiplied by that, and then at the end multiplied by 4 over 3. Oh yeah, I knew it would do that, I knew it. Okay, so let's do this like this instead. So we've got 4 over 3 times by pi times by bracket 0.25 cubed. So that's just the back end of the equation. Now when it times up by 1000, I'll probably see this could be again an incorrect answer. Actually no, it's not that far off looking at it. Oh, I read it incorrectly. I was thinking it needs to be that. Well no, you can see that's less than that, so that's fine. So we've got that. So not as bad as I thought on my calculator. It's less than 1 times 10 to the minus 7, so that's all good. Calculate the raindrop's terminal velocity. Assume that the upthrust from the air is negligible. Explain the work you're working clearly. Okay, so you've got a viscosity there as well. So if you want terminal velocity, remember you've got to use Stokes' law equation. So if it's at terminal velocity, then weight is equal to viscous drag plus upthrust. If it's a falling object, we're saying that upthrust is negligible. So you're just having the mass of this raindrop is equal to F, which is equal to 6 pi r eta V. So they want V, so that's going to be equal to mg over 6 pi r eta. Okay, so mass of this raindrop we've just got already. When you multiply that by 9.81 and then divide the whole of that by 6 times by pi times by the radius, that's 0.5 times 0.5 times 10 to the minus 3 and then times that by the viscosity, which we've got over here. Okay, so let's write that out so you can see it. So that's my value from above, which is 6.54. 6.54 times 10 to the minus 8. So if you didn't get this, you could have used this value here and they would have accepted that in terms of your working. Times 9.81, and you can divide that by 6 times by pi times by 0.25 times 10 to the minus 3 times by eta, which is 1.8 times 10 to the minus 5. Yeah, times 10 to the minus 5. Okay, so let's work that through. So I'll just continue from here. 9.81. That's my top line done. Now I want to divide that by 6 times pi times 0.25 exp minus 3 times 1.8 exp minus 5. So lots of long numbers. This is why it's a 3-mark question. So I end up with a velocity of about 7.57 meters per second. 7.57 meters per second. Okay, so you can see how I've worked that out there. I've just written everything out from that expression there. Rearranging that for that. Just getting rid of the f because we know the f is equal to that. Putting my values in. You can see there, and you end up with that value there. So we'll check that on our mark scheme. So we've got a few questions to check. So how far do we need to go back? Yeah, we need to go back through question 3 and 4. Is there question 5? Oh, and there's a little bit left of this. I might as well go through that and then we'll go through the whole thing just to double check. Sketch a graph to show how the raindrop's velocity increases. So it's velocity against time graph. Okay, so velocity time graph's got a very straightforward shape to it. It should go like this. Okay, you can label that speed if you want as 7.57. Okay, so there you go. So you have that shape to it, and you can label the speed if you want. Okay, experimental terminal velocity will be different for a larger raindrop. Okay, so for a larger raindrop, let's look back at this equation over here. The mass would be larger, but the radius would be larger as well. Okay, we know the link between that and that is the mass is going to be linked to this idea of an r cubed relationship. Okay, so it's going to be r cubed as a key factor as part of this, or this is just r, so it's going to be an r squared relationship. So essentially velocity is proportional to r squared. So what that tells us, so mass is related to r cubed, radius is going to be related to r just by itself, so you end up with r cubed over r, so you end up with r squared. So velocity is related to r squared, so essentially if the radius was twice as large, the velocity would be 4 times as large, because if r was 2, then this would end up being 4. Okay, so if the radius was twice as large, the velocity would be 4 times as large. Okay, so we'll work through from the last question, this question 4. Okay, Vt increases due to greater mass. That's the idea here, but I went through in a bit more detail, so that's fine. Okay, so straight line, line drawn, and then curves correctly to horizontal, scale on axis. So cool. You've got to put that scale on there. Okay, you've got to put that scale, that value that you figured out, whatever value you got was there. So they've got times was 0.56. Okay, that's because they didn't carry it forward. Same value as well I've got there. Okay, so you can see that we worked for this correctly. The explanation was the same idea as us, what we said, and you can see that we got about that value there as well. Just double checking where I wrote that out. Yeah, 1.96, exactly the same as what it was, so that's approximately 2. And in question 3, okay, you can see that they worked out the same, using the same sort of idea. They just did the rearrangement first of force is equal to weight minus substance, which might have worked, which would have worked, might have made it easier. There's the link with velocity. There's the idea in terms of the arrows. And there's the idea in terms of the expression for upthrust. Brilliant. So, oh yeah, there's the other expression, the relationship between forces, which is everything I just missed. I did go through that though. Brilliant. So that is the end of video 1 for ISP task 1 on materials. Okay, next time I'll go through video 2, which is all about, if I remember correctly, Hooke's law, which is a very straightforward principle. Let's just double check. Yep, next time is on Hooke's law. Thank you very much for listening, guys.